Hello and welcome to this class on Huffman coding or Huffman Trees compression. In previous classes, we've discussed the advantages and disadvantages of compression in general, looking at the different types. And in the previous class, we looked at a simple method of compression, RLE. In this class, we're going to look at something a bit more complex and a more effective way of reducing a file size or compressing data down into something a bit more compact. And to do that, we're going to use Huffman trees. And I'll just need to share my whiteboard again. Now, Huffman trees, you might actually hear it being referred to as Huffman coding as well. Okay, Huffman coding happens in two parts, and it involves making a tree. Okay, so we first build our tree and then we put it to good use. But let me give you a little introduction into why Huffman is still relevant today. Well, say if we've got the alphabet, okay? Say we've got A, B, C, D, E, for example, okay? We've got the whole alphabet and we're going to look at trying to represent these characters using binary, but in a very effective reduced manner, okay? So for example, we might give A 1, okay? So when you see 1, it's an A, and we'll make B a 0. That's fine as it is, but come C, well, we can just make it 1, 1. And like D, we can make that 0, 0. But if a computer was to see that 1, 1, how does it know it's C and not two A's together? You see, this is where the confusion lies. But Huffman allows us to represent characters with the minimum amount of bits that are unique, and they avoid this confusion in terms of whether it's 2 letters together or just 1. It's really clever, but a little tricky to get your head round to start with. So it might be worth going through this video from start to finish and then trying a few examples when you replay it yourself. Okay, so let's begin building our Huffman tree. Okay, so here we are. We are going to pick the word football again. Okay, like I said, it is a favorite with compression questions, the word football. So we're going to compress that down. Okay, using Huffman. The first thing I do is count how often letters appear in the word or paragraph or sentence or whatever it is. In this case, it's characters, it's a string. So for example, we got 1 F and 2 O's. We always start with the most frequent letter. So let's start with, we got 2 O's. Okay, we also have 2 L's. So I'm going to put that on the list, and the rest we got like 1 F, 1 T, 1 B, and 1 A. Okay, so I've laid them all out. I've ordered them in frequency order, with the most frequent letters appear at the top and the least frequent at the bottom. One thing to remember, that if you are compressing a sentence, don't forget to include the spaces as well. Okay, include the spaces, treat them as a character as well. That's really important to remember. Okay, so let's start building our tree. Now, we start with the low-lying fruit, okay, the least frequent letters. So I've got F, T, B, and A because they all occur just once in our word that we're compressing. So I'm just going to lay them out here. So we've got an A that occurs once. We've got a B that occurs once. We've got a T that occurs once. And finally, we've got an F that occurs once, okay? And we can pair these up. We can group these up. So 1 + 1 is 2. 1 + 1 is 2, okay? So we're now at level 2. So we go to our frequency list, and I'm just going to cross these off so we don't confuse ourselves. And we do actually have letters that occur twice. So I'm going to add these to level 2. So we've got L, which occur twice, and O's, which occur twice. And we will repeat the same process. Okay, we pair those up. 2 + 2 is 4. 2 + 2 is 4. Okay, cross them off our frequency list. Have we got any more letters to add? No, we don't. We're at level 4. Say if you've got letters that occur 3 times in a word, okay, you can add them in here and pair them up that way. You can bring them in at that level. You can draw a tree in different ways, and it will still work. But for me, in this example, I don't have any more letters left, so I'm just going to add these 2 together. 4 and 4 is 8. And that's our tree. That's what we call a Huffman tree. I guess if you looked at it from a different angle, upside down, for example, it will sort of resemble a tree-ish. And this is what we're going to use in order to encode the word football. But if our tree is incorrect, then our final answer is also going to be incorrect. So what I advise you to do is that top number, in this case 8, this is a quick way of checking that you've done it correctly. 8, that top number should correspond to the number of characters in what you're going to encode. In this case, football has 8 characters and 8 is the top number. So I'm happy my tree is in place. Now, this is the fun bit. This is the fun bit. So I'm going to write football down the side like so, okay? And we're going to generate the binary equivalent for each letter. Now, I'm going to put a 0 and a 1 here, okay? All will make sense in a second, I promise. So if you notice, the 0 is on the left branch and the 1 is on the right. So any branch on the right is a 1 and any branch on the left is a 0. Okay. Now, imagine this tree to be a marble row, and we have our marble. I'm going to have a red marble. Here's our marble. Okay. And we're going to drop that marble at the top of the tree like that. Okay. We need to first encode the letter F. So find the letter F on your tree. Okay. It's at the bottom here, circled. And we're going to drop our marble and we're going to follow the marble's route until it stops at the letter F. Okay. So we drop the marble in and it's going to go this way first. It's going to go down a right branch, isn't it? So it's going to be a 1. It's then going to take this branch on the left, which is a 0. And then finally, it's going to take another right branch, which is a 1. So F is represented by 1, 0, 1. Okay, let's rewind that and let's do another example. We need the letter O, because it's the next letter in our word. So find the letter O in our tree, which is here circled. We reset our marble, drop it down, and we follow its route. It first goes this way, so it's a 1, and then also another right branch, another 1. So 1, 1 represents an O, and I can just repeat it because there's 2 O's. Okay, pause this video and have a go at coding T and B. Okay, so hopefully you've had a go at encoding T and the letter B using my Huffman tree. Let's see if you were right. Okay, so our next letter is T. So here it is circled. Okay, we're going to drop our marble down, follow its route. So it's going to go right, left, left, which translates to 1, 0, 0. And if we do the same for B, we've got a left, right, right, 0, sorry, that looks like a 6, 0, 1, 1. The A is here, so that's going to be left, right, left, 0, 1, 0. And finally, we've got the L here, which is a left, left, which is a 0, 0. There we go. So we're able to encode our word football using the Huffman tree that we built a moment or two ago. And if you want to see something really impressive, you can Google Huffman encoding and see examples where people have encoded whole song lyrics. Like the tree is huge, it's amazing, and they encode like stories and books and complete novels. It's a work of art in itself. We're just sticking to something small, and most likely if you ever get a question on Huffman coding, it is going to be something pretty simple, like a single word or a sentence or two. They might give you a Huffman tree to work with, or they might get you to draw one from scratch like we've just done in this example. If they do give you an example Huffman tree to use, they will always just indicate whether it's a 0 to the left or a 1 to the right. They're not here to catch you out. They're to give you as much information as possible so you can demonstrate your understanding of this compression method. Another form of question that you might get to do with Huffman coding is to calculate how many bits it's been reduced by. So they'll say, if every letter in my word football is represented by 8 bits, so we have 8 by 8, 8 bits by 8 bits per letter and 8 letters. So we have 64 bits in total. Yeah. Can you calculate using Huffman how much you are reducing it by? So here are all our bits here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 bits. Okay, so we've gone from 64 bits originally, and we've managed to compress it down quite considerably down to just 20 bits. Okay, so there are various flavors of Huffman tree questions that you might get asked, but it's always beneficial to learn the process from the very start through building the tree to encoding something and then working out how much you've managed to reduce it down by. Okay, if you've learned that process from start to finish, you can't go wrong. So why not have a go at encoding something different? Maybe try your full name, maybe try your address, for example, your postal address, and see how you get on. If you get stuck, then just simply replay this video and take your time building the tree, learning how to check that your tree is correct before proceeding to the encoding part. But yeah, I hope you find this class on Huffman coding useful. Take care. Bye-bye.